Welcome back. We are talking about section 2.4, the chain rule. So it doesn't break up perfectly along learning objectives here, but we will certainly discuss the chain rule in this first video, and then we'll follow up with the use of the generalized power rule in the second video. So the chain rule doesn't quite have the same evocative name as product rule and quotient rule, but it's basically what among the class of what I would consider sort of the higher order rules. So product rule and quotient rule, the rules you use if you have things getting multiplied together in some function or things getting divided, these are ways to get you to other rules, basically. They never really fix it all by itself. So using product rule gets you down to two smaller derivatives. And then you use things like power rule, for instance, to actually resolve those little derivatives. Quotient rule does the same thing. Chain rule is yet another one of those. It gets you to some smaller derivative calculation. So the thing that's challenging about chain rule is it has to do with composition of functions, and that's always been tough for us. So composition is just a challenging topic by itself, and chain rule attempts to demystify the derivative of a composite function. So if you think how product rule and quotient rule were sort of a challenge, this is sort of another whole ballpark because we're already familiar with multiplication and division without too much trouble. Composition is another story. So if we start with some function, and the notation gets a little odd, but we'll try to be consistent about this. U, we're imagining, this letter U is supposed to be some other function of another variable. So U is a function of x. Each of these things is differentiable because we need all their derivatives. So basically this says if you want the derivative of the whole deal, f prime, all the way through to this input variable x, first you take the derivative with respect to U, and then you take the derivative with respect, you take the derivative of this kind of inside function with respect to x. So the chain in chain rule is this multiplication. We take one derivative and then we sort of tack on another derivative. And then when things get really bad, although they won't very often, we might have to tack on a couple of different things, and hence the chain. You get more than one link in this multiplication, which kind of evokes the notion of a chain. So the derivative of this composite function is the derivative of the outside things times the derivative of the inside thing. All right, as always, it doesn't make any sense till we get an example. So let's try one product, well, could be written as a product, but one derivative without using chain rule. We use algebra to get around it. So here's the thing we're trying to take the derivative of, but before we do any of the derivative stuff, so this d dx is still hanging out here, we multiply out everything on the inside. So this is just distributing 2x minus 1 times itself. So we get 4x squared minus 4x plus 1. Now, there's nothing fancy we need here. We can do this just directly from power rule. So the 2 comes down to give us 8x, derivative of negative 4x is negative 4, and derivative of 1 is 0. So now what we have is an answer to compare to when we try this using chain rule. So we should get an answer of 8x minus 4 through this other strategy. Okay, so now if we try chain rule and think, now the strategy is we're envisioning that this stuff inside the parentheses here, 2x minus 1, is some inside function, as it were. So what's happening is, just algebraically, we would take 2x minus 1, and then the last operation is that we would square it. So we're just going to basically picture 2x minus 1 all squared as something squared, u in this case. So here's the 2x minus 1, and here's u. This is just a rewrite. There's no actual calculus that's happened. But how this is supposed to be helping us is, now if I look at this expression, I see that it's just u squared. Well, gosh, I can take the derivative of something squared without too much trouble at all. I know that we start with u squared, and we're going to get 2 times u when we're done. So the catch is right here. This was not asking us to take the derivative of this thing with respect to u, in which case we'd be done. 2u would be our final answer. We're envisioning that this u actually is some more complicated thing that has x's in it. And the only reason that we got to pass through this x as the input was the chain rule told us, it let us basically, take the derivative of u squared as though this were just u to begin with. But then the price we have to pay is that we're supposed to tack on the derivative of the inside stuff. Well, the inside stuff that we've been ignoring for a minute is this blue underlined 2x minus 1. So chain rule forces us to tack on, and by tack on I mean multiply by, the derivative of this 2x minus 1 thing. So derivative of 2x minus 1, now there's no trickery. The variables match up. They are x and x. And so the derivative of this thing is a not super complicated 2 when we're done. So we had the 2u out in front. We've got the 2 from the derivative we just computed. So 4 times u is a reasonable answer, but 4 times u written in terms of x's is all of this stuff times 4. So if we take all of this stuff times 4, we get 8x minus 4. This is just written in terms of x's instead of in terms of u's. So if we really want this, we have to state it pretty explicitly. Write your final answer with x's in it. Or maybe if it shows up as a multiple choice question, it might only have x's in it, so you'd have to go back to the original variable. And this is kind of the polite thing to do anyway, because notice that our original answer had x's in it, not u's anywhere. So our final answer should probably have x's in it as well. The final thing we should find sort of comforting about this is simply that the way using just expansion, we got 8x minus 4, and then using this fancy new rule, we got 8x minus 4. So at least in this example, the processes were consistent. But in theory, they should always be consistent. Okay, now, I'm not claiming that we should always do this, that we should take something simple and make it really grandiose and complicated. But there are instances where we have no choice but to use chain rule in order to implement this. So instances like the following. So we've got y in terms of x. So no context for these variables yet. We'll get to the word problems. Don't worry about it. We'll get to word problems. I'm sure that was the top of your list of concerns. So y is x cubed minus x, and then x also depends on this other variable t. So x is 1 minus 3t. And our task is to find dy dt. This is why I sort of threatened earlier on in the term that I would try to be consistent about also using this notation and using the whole ddt thing as we run along. Because now as the variables start to get confusing, what is the input, what is the output, then writing this in the denominator helps remind me that t is ultimately the input. So this tells me I want the rate of change of y with t as the input variable. And in particular, we're going to get to plug in a number when we're done, so t equals 0. Okay, so what we have is one expression for chain rule, and we're going to get another version of it using the Leibniz notation, this like dy dx kind of deal. So y is a function of x, x is a function of t, and another way to write chain rule is the following. So this looks like a lot, but here's what it's saying. dy dt, this is the derivative of y with respect to t. This says if you want to get that rate of change, it's the same as rate of change in y with x as the input variable. And then all you have to do at the end is multiply by dx dt. And so here's the thing to keep in mind. I have an equation that relates y with x. So this derivative is something I can do just from that equation. And then we have another equation that relates x and t. So each of these two pieces is something available to us without too much trouble. All I have to do is take those answers and multiply together. Okay, so using this writing, it's not a different rule or anything, just this different way of expressing chain rule. We've got our two things to compute. So here's our derivative of y piece right there. So this just goes back to that equation they handed us and says, here, y really is x cubed minus x, so now tell me what the derivative is. We've also got a relationship between x and t. So this is going back to the beginning of the problem in the statement where they just told us x is 1 minus 3t, so what we really want is its derivative. So again, really, the t's and the x's, it's really important to note what is the actual input variable here as we go through. Okay, so the derivative of x cubed minus x, so power comes down, 3x squared. Take the derivative of x, we get 1. And then we've got 1 minus 3t, so derivative of all this stuff, just negative 3t. And this is a pretty solid expression, except that ultimately we're going to have to plug in a number for t, and t is the input variable anyway, so x's seem sort of lazy. So we'll go back to t's. And this is expressing x in terms of t's instead. Still making use of that x equals 1 minus 3t equation. Now, we could simplify that, but we've got to plug in t equals 0 anyway, so we might as well just leave this how it is, plug in a number and then get our final answer. Do a computation once instead of simplifying all this, then doing another computation. So if we let t be 0, then this all inside here is just 1. 1 squared, okay, still 1. 3 times 1 minus 1 is 2. Negative 3 times 2 is negative 6. So this is the use of the chain rule in kind of the purest form we can come up with. I'm not claiming that this should make a great deal of sense just yet. I'm hoping that some word problems will make this a little tidier. And it turns out that we revisit some of the more challenging aspects of chain rule again in 2.6. We just call it something a little bit different. So before our next exam, we'll have a chance to practice this in a couple of different sections. But we'll come back in one more video with the generalized power rule and everybody's favorite, a great word problem.